These are electromagnetic locks. They're used for things like, well, a good example, the Amazon lockers. Have you ever seen the Amazon lockers that you order goods, get it sent to the suitable Amazon locker locally? And when you go up, you can scan your phone or type in a number, and there's a click, and the door of one of the lockers does this. It basically unlocks and it pings open, and it physically swings open. You can go and take your goods out, and then you close the door and it latches shut, and that's you got your goods. It's very good. It's a great way of picking stuff up if you're not like to be at home. So this is the type of mechanism you'll find in these, and they operate at 12 volts, but there's a few things you should know. This is the same sort of mechanism, but this one has a spring plunger. The reason it's got a spring plunger is to push doors open and make sure they don't swing shut again. It's just a bit of extra oomph to get the doors to open. But it's the same principle. There's a solenoid in the back, and it pulls down and it kicks the plate out and the door swings open. Let me show you these operating electrically, and this is going to get very noisy. There's going to be very loud clicks because it's quite spicy. So these ones operate at 12 volts. I've hooked up some leads temporarily. So I shall hook this up to here, and it will eject. As soon as I touch this on, it will eject the pin. And it ejects it right across the table. Both incidentally use the same pins. Likewise, when I connect this one up, it will fire the pin out, and that's it unlocked. It's worth mentioning that this one draws a lot more current, this little one. They're very short duty cycle solenoids. They're small solenoids that punch quite a lot of force to actually unlock that reliably. This one draws about 3.5 amps at 12 volts, and this one draws about 2 amps at 12 volts when it's pulling its slightly bigger solenoid in. It's also worth mentioning that you can't leave these energized for any length of time. I'll show you the circuitry to be used to drive them later on in the video, but they're only rated for a 10% duty cycle, but in reality, their operation would literally be once or twice a day, depending on the use of those lockers. It would just be a brief pulse, and that would be it. That's how they're designed to be operated. They're not designed for sustained current. So I can show you the rough interpretation of the mechanism here. There is the swinging lock here. Now, if I can actually operate this with a screwdriver from down below, I can show you this going. When the pin comes in, actually, you know what? I'll just use the hasp that it's supposed to go take. When the pin comes in, you'll see that as it pushes that back, a little lock comes up, a little pin. It's basically an arrangement like this, where this is that hasp, and as you push it in, this pivots up. And as it swings back, if the blue is the channel oh, zoom down this, it's probably better. You'll see better. If the blue is the channel, the slot that this goes into, that's what's out of sight inside the unit. There's the long arm, which is the locking arm, and there's this one, which is the one that comes up and catches the pin and stops it being pulled open. In its open state, that pin is free to move in and out. But when you push it in, it pushes this back, and then there's this arm on top, which you can see this metal plate, this pivoting metal plate, and it's got a little square cutout. This bit drops into that square cutout. So once it's pushed in, that clicks down, latches it, and that's what stops it coming back out. When you activate it, you can see the solenoid at the back here pulls down, and it pivots that up and allows that to click back out. This one is riveted together. The other one is held together with screws. I'll show you the circuitry that's like to be used to draw these, and then I'm going to take the screws out of this, and we'll see if we can open it without it flying apart into millions of pieces. It might happen. Something really important. Dave at EEV blog mentioned this recently. The flyback protection diodes. I've mentioned them a lot in other schematics as well, but really important for this one because of these high current coils. I've shown an ordinary transistor here. These days you'd use a MOSFET. You could actually use something like a ULN2803 style sort of pack of MOSFETs, Darlington should I say. But these days it'd probably be a MOSFET, but I've just shown a generic transistor. To control this, you'd basically send the signal to the transistor, but just very briefly, just to turn it on for as long as it takes to unlock the mechanism and fire open. But when it does so, this end starts off being positive, it gets pulled down to negative, and it builds a magnetic field in that direction in the process of unlocking it. The diode is very important because When you turn it off again, this end will go positive, this end will go negative, and it can create a massive, because it's got no load in it, it can create a really high voltage spike that can destroy the transistor. So that's why this diode's here. The diode normally does nothing because it's in the opposite polarity to the 12 volt supply. But when that magnetic field is collapsing, it takes a shortcut through that diode, and that basically quenches that spike. It's a sort of flyback diode. Very important. Another thing that would be really useful to add here, if you had a load of these solenoids on, say, one common bus, it would be useful to add a PTC fuse in line, rated for, say, just under the operating current of the coils, because they are operating very briefly. The PTC fuse would protect against the processor crashing or the transistor failing and burning out the coil. Because what would happen is that if it was just operated briefly, the PTC fuse wouldn't generate enough heat to actually go into its latching off state. But if the coil jammed on, this fuse would kick in and it would basically go high impedance. It would limit the current through until the whole system had been reset and the fault had gone, and then that would cool down and reset again. Just things worthy of note. In the past, I would also have used, if I was using an ordinary transistor, maybe a capacitor in series with a discharge resistor across it, a high value like 100k. Across that, and say this would be, say, 10 microfarad. What that means is that when this went positive, current would flow to charge that capacitor, and it wouldn't be a nice square wave, but it would give it a controlled pulse to turn the transistor on. But then after that capacitor was charged, you'd only get a very small leakage through this resistor. So basically speaking, the transistor would only be able to operate for a brief pulse. I used to do that. I used to just play safe. I used to go too far. But it's better going too far than having terrible faults that occur, like a software update that results in all the solenoids burning out. People will have been there. Let's undo some of these screws. Let's use a smaller driver. What have I got here? That's too small. This one looks promising. Is this going to ping apart? I do hope not. But then again, it'll be a good exploration if it does. The Amazon lockers are great. When you just can't get stuff delivered to home or work, it's nice if you're living or you have to pass through the city centre if you're commuting to a job, because you can't really drive to it in the case of some cities. It's useful maybe to just order it and pick it up, particularly when travelling away from home. This is promising. There it is. Oh, I forgot to mention something. This switch. This is showing everything, isn't it? This is showing absolutely everything, and it needs brightened up. This is where it's going to be super bright, but I don't care, it's fine. That's going to be super bright, and I'm going to look like Mr. Honky with his white fingers here. Here is the latching mechanism. This one doesn't have the hole through the plate like the other one. I've just pinged the spring off. That's all right. I can put that back. I'll just leave that out at the moment. So when this goes in, there's that switch there. The switch will, as this pushes back, it lets go of that switch. Then this goes under the ramp and it clicks in, and that's what holds it. Now that switch, because it's closed, because it's using the normally open contact, normally closed contact, because it's now released, that switch is now making. I can prove that. I can prove that with the meter. I shall bring the meter in. I shall set it to continuity. And I shall bring in the lead here that comes from that switch, and I shall probe it and it will go beep. It's beeping. And then when that solenoid activates, this is where it's going to get noisy. Hold on, let's see if I can get my probes back in here again. It's all, the wires are quite stiff. They're not playing ball at all. When I press this down, oh, it pings it out. And because I've gone far too far and the switch has fallen out, yeah, that wasn't a very good demonstration. But this is what happens. Actuating that while it was open was probably an absolutely terrible idea. It's gone way too far. Yeah. Oh, it's just little dimples down here. It really needs the case to be screwed shut to actually hold that in. It's just, blimey, look, it's just dimples on both sides that hold that switch in. But nonetheless, there it is. It would... that's the position it would be showing that the door was closed, and then when this comes down, it opens it. This is a screw. I tried unscrewing it. It didn't unscrew, but I didn't know what was inside. I do now. There's a fairly powerful spring up there. And this one also has a very powerful spring because it's the one that's designed to push that open and make it ping. Would you like to see it activated electrically? Yes, you would. Right, well, let's activate it electrically. Pow. Very noisy. Quite a loud click. I'm not sure how secure they are, but I will say that I got a big mofo neodymium iron boron magnet and I just held it all around the case. And it, I'm going to tame this down again. I held it all around the case and I couldn't activate the solenoid with the magnet. The magnet stuck to this steel case, but that was it. I just couldn't, it's kind of shielded. They've obviously thought of this of people applying external magnets. But that's what's in these. They're quite interesting. They're quite nicely made. I shall provide links to the company involved. They have data sheets showing various things, including the duty cycle and the voltage rating, 12 or 24 volt optional, and the current 2 amp it was. 2 amp for this one, but 3.4 amp, that's absolutely right. That's exactly what I measured it at, because it's got a very low resistance. But interesting things. Well worth getting some of these and exploring them. I shall put links to the site though, and I think these may have come from Banggood or eBay or something. I'm not really sure, but they weren't that expensive at the time. Certainly they're quite a novel thing for, say, secret hatches and things like that for remote control. Novel devices.